Hello everybody, welcome to Marketing Analytics course. This is Dr. Shagata Chatterjee from VGSOM IIT Kharagpur who is taking this course for you. And this particular class, which is in week 9, last session, we will discuss about survival analysis in case of customer churn. So, what is survival analysis? So, you will see that this is a survival probability curve. So, it is actually talking about that every time period, if you are alive today, what is the probability that you will be alive tomorrow? What is the probability that you will be alive day after tomorrow, and so on, 2 days later, 3 days later, 4 days later. So, how much is the probability that over a certain period of time you will be alive? And this is something which is important to know, because certain times it is in the context of, let us say, customer lifetime calculation, that what I will take as my customer lifetime, this is something matters. So, survival probability, you see that initially 80% of guys survive beyond 7 years, and then at this point, which is the green point, it is 50% of guys who is surviving after 8 years. So, area under the curve is basically the expected survival time. So, if I can give you information like this, that the probability that your lifetime L is greater than t, if I can give this particular probability, that what is the probability that your lifetime will be greater than t. So, that is particularly this particular graph. So, that is something that I am giving, and then t into this thing, summation of that, or in this case integration of that, if by chance if it is continuous distribution, that is basically your expected lifetime. So, expected lifetime. So, if I can by chance get this particular probability, if I can find out what is the expected lifetime, then that is something that I can use for customer lifetime value calculation, because you see that whether I can do the calculation for 5 years or 6 years or 10 years, what is the value that I will do is sometimes come from here, this kind of an analysis, that how much you are considering as expected lifetime. So, there are various other cases where these particular things apply. For example, it can also be applied that how much will be the time taken before you die if you have coronavirus, let us say. So, in certain cases it is much low, in certain virus cases it is much low, in certain viruses cases it is much high. Or how much time will this particular thing, what will the probability. So, let us say in general we have a probability of living up to 60 years, 70 years, 80 years. But given that you have this particular disease, what is the probability that you will live, and how that changes, how that probability changes over time. So, let us say if there are two curves which looks like this is for probability, this is time, this is for curve 1, this is for curve 2, which is group 1 and group 2. You will say that as time increases, as you gets older, your probability of living comes down obviously. But for C1 group of customer who, let us say, are cancer patients, are much lower than people who are not cancer patients. And here the ratio is the odds ratio, or not exactly odds ratio, the hazards ratio is much less, and here it is much higher, let us say. So, once you get aged, the impact of cancer on your probability of living is much higher, and that is something that we sometimes want to see. Now, in this case it is not cancer, we are talking about customers. So, given that there is some service failure, the older customers will be having higher chance, or the loyal customers will have higher chance to stay back, and non-loyal customers will be having higher chances of going away. So, if I can find out that loyalty curve, and you can find out that what are the various aspects which impact your decision of staying, surviving as a customer or not surviving as a customer, or staying in this particular company or not staying in a particular company, then that can be analyzed using these survival analysis techniques. So, what are the key issues? The key issues are, so how the likelihood of a customer churn changes over time, and determine the potential intervention points. So, at what point you should intervene, and questions if it can answer is how many years, months on an average do the customer stay. So, if I do not do anything, how much will leave the customer in my service. And how long do male customers stay compared to female customers? So, is there any difference between gender? Is there very difference between nationality? Is there any difference between one customer group and another customer group? So, this is something that I can try to find out using this particular technique. And is our understanding of customer life cycle accurate with reality? So, this is something that I can also try to find out, that whether whatever we understand about the customer life cycle, is this the case also. So, survival regression allows us to apply a model to the survivor's analysis to predict when an event is likely to occur. So, these are basic issues in which this particular analysis technique works. What are the key issues? What we can do with it? So, we can model the relationship between customer churn, time and other customer characteristics. This is something that we can do. And we can also answer this kind of questions, that what is the probability that this customer who is a female non-senior citizen with dependents will stay for 2 years, and what are the significant factors that drive churn. This kind of answers I can give. So, there are basically lots of applications in telecommunication. This is a huge application. It has application in insurance, mortgage, mail order catalog, retail, manufacturing and public sector. So, there are lots of places where it has a, so for instance, manufacturing, it has a application is lifetime of machine components. In public sector, it is time intervals to critical events. In retail, time till food customer start purchasing non-food and so on. Now, we have two estimation techniques. One is Kaplan-Meier, which is very basic, which says that the probability of staying back is nothing but the probability of leaving given that you have lived the first time. So, it is saying that every time period, the factor that you will be living in time period 2 is independent of whatever was your probability that you will be living in time period 1. But, so switching, so from time period 1 to time period 2, this switch will not depend on the probability of time period 0 to time period 1. So, that is something that they are saying, that you will survive from time period 0 to time period 1 has no impact that you survive, that you will time period 2 given time period 1. But it is also saying, the maths is also saying that the probability, if they are not independent, then the probability that you will survive time period 2 is time period 0 to 1 into time period 1 to 2. Fair enough. Probability of 1 is probability of 0 to 1, this transition, stage transition. Probability of 3 in that case is probability of 0 to 1 into probability of 1 to 2, and then probability of 2 to 3, these state transitions. So, then probability of t is basically probability of t minus 1 into probability of t minus 1 to t, this state transition will happen. So, then if I go on doing this maths, then probability of t is nothing but probability of t minus 1 into 1 minus dj by nj. What is dj? dj is number of deaths at that time period, and nj is total number of people. So, that is what this particular formula is saying. If you check this formula is saying that ST, that your survival rate is nothing but survival rate at t minus 1 into 1 minus dj by nj. So, that is the formula. dj is number of deaths. So, this is the probability of being dead, 1 minus that, this is probability of being remaining alive. So, the probability that you remain alive up to j minus 1th time into jth time period's probability of remaining alive is the probability that you will be alive till jth time period. Fair enough. And then the hazard rate is the change of this death rate, nothing but the change of log of this death rate. Why log? Because this is a probability which is very small number, 0.0000 something. If you take log, it becomes a little bit of handleable. Log likelihood we used to take, that is why. That if we take log, this 0.001 becomes 10 to the power minus 6. So, log of 10 to the power minus 6 is basically minus 6. That minus 6 number is still handleable than 10 to the power minus 6, which is a very small number. So, this is called hazard rate, the rate of change of log of likelihood of survival. Rate of change minus ddt of log of what? Log of survival rate. So, survival rate is basically probability of surviving. So, that is something, it is a non-parametric method we can calculate, and then we can calculate between two groups and show that one group has higher hazard rate than other group. So, one group's rate of survival drop is much steep, other group is not so steep. If that is the case, then I can say that these two groups are different. Another method is basically Cox proportional hazard method, which is say that this hazard rate is not only dependent on time, but also dependent on many other factors, and these x1, x2 are those factors. So, instead of two groups, you can take multiple groupings like age, gender, income together and say that all of this impacts the hazard rate. So, all of this impacts the rate in which you will drop. So, in general, your probability of living third year, fourth year, fifth year is this much, but if you have from higher income group, your hazard rate is much lower than a lower income group. In lower income group, the probability of surviving over some number of years drops in a much steeper way, so which looks like this. If I normally the probability of living at certain time period is high, at 0 time period. Slowly as you go on aging, the probability gets dropped. Fair enough, this is the probability of living, this is time. Slowly it goes down, makes sense. If you are at age of 95, the probability that you will live 96 years is much low, goes down. But this going down rate, if it is average for rich people and educated people and informative people, this is this, and for poor people it might be a little bit much lower than that. So, this is the change is much steeper, here the change is much flatter. So, this case, in the lower case, the hazard rate, if I say H1, in the upper case if I say H2, H2 is much lower than H1, the hazard rate is lower. So, that is something that I am trying to say here, that if the hazard rate is lower or the ratio of hazards is lower than 1, then there is a reduction of hazard. If the other case, there is an increase of hazard. So, there are two hazard functions that we find out, and then we try to check that the hazard ratio we try to find out. And you can read from this particular link about more about the survival analysis. But I will just quickly show a study which is for which you have to open this surf.r file. So, there are 4 libraries, I called the library, you have to install these libraries before if you do not have them. And the data that I will be using is basically the ovarian data, it is ovarian cancer data already inbuilt in us, and if you want to have a glimpse of this data, it has 26 observations of 6 variables, and this guy is the food time, FU stat, age, the residence, RX and ECOG. So, these are various kinds of factors which impact the chances of living, and this is the age, and this is FU stat, and whether this guy is living or death 10, and the time period at what time stamp this measurement has been done is something that they are checking. And the help of the description of this information will come here. So, you can get all the details. What is this? So, if time is the survival of or censoring time when you are measuring. This is the censoring status. This is age in years of and then this is basically residual disease present. 1 is yes, 2 is no. So, 1 is no, 2 is yes. This treatment group or control group, and ECOG is the performance status. These are some of the things that they are checking. So, what first do I do is I put these groups RX groups into 2 groups A and B. So, 1 and 2 I make them factor and label them as A and B. Similarly, ovarian residual, the death status is 1 yes or no, and then this one is good and bad. So, ECOG condition is good and bad is something that we are changing. So, 1 and 2 and etc. we are recoding. And now, if I just plot the age, this is the age. So, it seems like there are bimodal, 2 modes are there. It might be that is something that this particular thing is being shown. Then what I am doing is I am changing this ovarian data set. I mute it. Muted means it will change and put something here. But age group is, if the age group is higher than 50, then it is old, otherwise it is young. So, I am creating a new variable in this. So, which is basically ovarian age group, which is old and new I have created, and make them factor. Now, what I am doing? I am creating a survival data set. So, surv object is survival data set, time is equal to the time when you are measuring, and event is the few stat. So, that is the death or alive, that particular thing. So, I have created the surv object, which is basically a numeric variable, which is looks like this 59, 150, and plus or not plus is actually telling that whether it has survived or not. And then if I just feed it with Rx, so for two Rx A and B, it will be separately creating the charts. And if I put the summary, what it is doing, you just carefully see. First of all, it is breaking the data set for Rx is equal to A and Rx is equal to B. Two separate groups it is creating, Rx is equal to A and Rx is equal to B. And then what it is doing is that it is saying that what are the various time periods when some event occurred. When time period was 59, there was 13 people are there in RXA, and only one event, means one died, and then 12 were there. So, 12 by 13 was the probability from time 0 at 0 to time period 1. 12 by 13 comes out to be 0.923. Then in 115 time period, there were 12 people, another death happened. So, 11 by 12 was the death survival rate. So, what was the S2? S2 is S1 into 11 by 12, that means 0.923 into 11 by 12. If you do the calculation, it will come as 0.846, and slowly they went on calculating these survival rates. Same thing they did for Rx is equal to B also. Now, if I just plot it, you will know that this is how the plots look like. With probability 0.3 they are different, and if I just zoom it up, you will see that Rx is equal to A looks like this, Rx is equal to B looks like this. Can you tell me which one has higher hazard rate? Obviously, the graph which is at the top has the higher hazard rate. So, Rx is equal to B has much lesser hazard rate, the one at the top. So, Rx is equal to B has much lesser hazard rate than Rx is equal to A. And but on the other hand, P is equal to 0.3, this tests that whether these two are significantly different or not. P lower than 0.05, they are significantly different. P higher than 0.05, they are not different. So, as per my statistical analysis, at least I can say that these two are not very different. If I do the same thing for resi.ds and then plot it, now it is 0.057. So, at least at 6% level they are different, if not 5% level. And see, when resi.ds is no, less survival rate, when it is yes, very high survival, very high hazard rate, very much less survival rate is something that we can see here, at least based on the data that we have. So, till now we were doing the first method. In the second method, in the Cox proportional hazard model, we can actually have multiple. So, it is the summation of beta xx, and you have to, the equation is given in this particular in our PPT, and from there you will understand that what this mean. So, I am just plotting it. So, if I just run this much and see what this fit dot Cox pH say, it is giving the F coefficient, beta coefficients value there. This is the beta coefficients value for RxB and corresponding standard error of the coefficient, and then corresponding z values of the coefficient, and then it is also giving the p value of the coefficient. So, these three has effect, Rx, resi.ds and age group by Young has effect. The ecological condition has no effect. So, I could have dropped that in the model. So, by two ecological condition is not creating any different hazard rate for the groups. And if I just plot the GG forest, this is how it looks like. You would see that for Rxa and B, when I am saying Rxa and Rxb, two groups, this guy has, if keeping this as reference, the hazard ratio is 0.25 and significant level is 0.032. So, this is significant. On the other hand, hazard keeping receipt DS as reference, no, the ES is 4.25 and it is upper limit and lower limit, and it is also significant, very highly significant. Okay. And then if I say that old, so that means here I am saying that the group B 0.25 means hazard ratio less than 1. Less than 1 means group B is less affected. I would say keeping everything else constant, group B will have lower hazard ratio than group A. How much lower? 4 times lower, I would say. So, ratio will be 1 by 4 and that is significant, and here it is 4.25 by 1 and that is also significant. Here it is 1 by 0.11 means basically this ratio means 1 by 9. So, the young people has much less hazard ratio than old people. I am not giving this example in the context of our customer behavior, but similar data you can create from the customer behavior also. And for EcoG, the bad is 1.8 means by chance this EcoG is bad, you will have 1.8 times hazard ratio than when it is good, but this is not significant. So, I can probably ignore this result. I have to consider this result and this result, because in all the cases this is lower than 0.05, but in this case I can probably ignore. So, that is how we can create survival analysis. This is highly applicable in checking that how much time a customer will be staying with me, or how much time when I can do the intervention, which kind of intervention reduces the hazard rate. So, like here we are saying that whether Rx or age or something else is impacting the hazard rate. You could have seen that, let us say if customer lifetime is your value that you are checking, and every time period after 2 months, 3 months, 5 months, 6 months, whether the customer were there with you 1 or 0, that was your hazard rate calculation. Then you could have find out that what impacts your hazard rate. You did some intervention in January, the customer is still alive on September. You did another intervention on May, this is also staying back in September. Which one has an impact? The intervention in January or intervention in May? Which one actually made the customer to stay back? You do not know until and unless you do this Cox analysis. So, Cox hazard model analysis. So, that is how we can also find out that how to calculate exactly the customer lifetime and how to increase customer lifetime. One is churn management, but churn is an immediate management. Sometimes you have to do something much ago so that the lifetime increases. So, how to do that, which one will impact, which one will not impact, can be done using Cox proportional hazards model. You can try out for other customer data. You can try out a churn data from your customer databases and try out whether that can be applicable here. So, that is where I will stop week 9. In week 10, we will start text mining, text analytics and etc. Thank you very much for being with me. I will see you in the next week. Thank you.